last lesson of the semester today, we're going to talk about some real life things that you use logarithms for, some modeling problems. Wednesday, we'll review for the final exam, so I'll give you lots more detail about the final exam on Wednesday. For now, I would just want to tell you it's about the same length as any other test, 7, 8-ish questions, somewhere in there. And you are allowed to bring 4 pages of notes with you to that final exam. Okay, so kind of have that in your head as you're preparing. The purpose of the 4 pages is so that you can reuse the 3 pages you made from the first 3 tests. But if you want to make them from scratch, that's totally fine also. And then our final exam is Monday, the 21st at 1 o'clock in this room. Project 4 is due today. Just put that in your folder before you go. All right. Let's look at these preview exercises together. So the median starting salary of a person with a bachelor's degree in the humanities or sciences is $34,000. The median starting salary of a person with a bachelor's degree in engineering is $68,000. How many times as much money does the engineer make than the social scientist? 2 times as much. Yep. How'd you come up with that 2? You can divide 68,000 divided by 34,000, or alternatively ask yourself 34,000 times what gives you the 68,000. So there'll be a question later where you have to think about the how many times bigger. So it's just a little intro to that. Can you give an example of a number that might be used to report the magnitude of an earthquake? 7. What's another thing you might hear? 7 point something. Yeah. Yeah. So the Richter scale numbers, these are numbers, we're going to talk about what these numbers mean today. So logarithmic functions are often used to scale very large or very small numbers into numbers that are easier to understand. Because remember, a log is an exponent, right? So a common log is an exponent on 10. So taking common logarithms is a nice way to think about really large or really small numbers. Instead of writing it all out, you can just think about 10 to what power is it, right? Because then, like a million, the log of a million is 6, whereas the log of 10 million is 7. So instead of having to write out a 1 with 6 or 7 zeros, you could just say 6 or 7. So one of these examples is the earthquake magnitude. So seismologists generally determine the Richter scale magnitude of an earthquake by examining a seismogram. And this is just a picture of one. And the Richter scale defines the magnitude M of an earthquake to be the log of I divided by S. I is the intensity of the earthquake as measured by the seismogram, right? And S is the intensity of a, quote, standard earthquake, which is the smallest detectable earth movement. So we're going to use this formula for magnitude. So magnitude and intensity are 2 different things, right? Magnitude are the Richter scale numbers you're used to hearing. Intensities are much bigger numbers. Okay, so the 1906 earthquake in San Francisco had a magnitude of 8.3 on the Richter scale. At the same time, in Japan, an earthquake with a magnitude of 4.9 caused only minor damage. Now, because we're used to seeing Richter scale numbers, we know 8.3 is a much worse earthquake than a 4.9. But just thinking about the size of those numbers, 8.3 doesn't seem that much bigger than 4.9, right?
Not the way that.
But yeah, the way the Richter scale works, those are very far apart, actually. Okay. So the question is, how many times more intense was the San Francisco earthquake than the Japan earthquake? So let's, San Francisco. We'll do a little analysis for the San Francisco one. I'm going to use my formula, M equals the log of I over S. I know the magnitude is 8.3. And they asked me about the intensity. So the I is what I don't know. And S is the intensity of the smallest possible earthquake, but they didn't tell me what that intensity is. So I'm just going to leave it as an S. I want to solve this equation for I, right? Because they asked me about the intensity. So I'm going to solve this for I for the intensity. So there's a little hidden 10 right there for the base. So if I change this to an exponential form right now, what would it say? Close. 10 to the 8.3 equals I over S. Yep. And then to get I by itself, just multiply both sides by S, right? Okay, so your intensity is going to be S times 10 to the 8.3. So you see the 8.3, that magnitude, it's actually a power of 10, right? That is measuring the intensity of the earthquake. 10 to the 8.3. All right, let's do a similar analysis for the Japan earthquake. So magnitude is the log of I over S, and I want to figure out the intensity of the earthquake in Japan. So I've got 4.9 equals the log of I over S, and I want to solve for I. So I start by switching to an exponential equation. There's a little hidden base of 10 there, so this says 10 to the 4.9 equals I over S. Multiply both sides by S, and the intensity of the earthquake in Japan is S times 10 to the 4.9. All right, so now the question was, how many times more intense was the San Francisco earthquake than the Japan earthquake? So this is like the question earlier, how many times much money does an engineer make over a social scientist? We just divide, right? The bigger divided by the smaller. So the intensity for San Francisco over the intensity for Japan is S times 10 to the 8.3 over S times 10 to the 4.9. The S's cancel, so that's why I didn't even tell you what number S stands for. And then how do you divide when you're dividing like bases? How do you simplify that? Subtract. So this is 10 to the 8.3 minus 4.9, which is 10 to the, well, 8.3 minus 5 would be 3.3, so 3.4. Let's get a number for that. 10 to the 3.4. $2,512 times as intense. Right, so that shows you that it was a much stronger earthquake. The 8.3 versus the 4.9 actually represents a difference of 10 to the 3.4 in intensity. Okay, so increasing the magnitude by 1 actually increases the intensity of the earthquake by a factor of 10. So every time the Richter scale goes up by 1, the intensity went up by a factor of 10. That's it. Now we have several other real life things that use logs to measure.